a metascheduler in the HPC domain, or a scheduler, DAG engine, and workflow management engine, which are all similar related terms. To help explain what Cylc is and how it compares to other systems and products in this space, here is a technical description. Cylc is a decentralized, distributed DAG and DCG scheduler, which is a bit of a mouthful. So let's go through each of those terms one by one. Firstly, Cylc is a scheduler. A scheduler is a system which allows you to define a workflow in terms of tasks, the actions that you want to perform, say retrieving data or running a numerical model, and the dependencies which represent the flow of data between the tasks. Cylc is a directed acyclic graph scheduler, or DAG scheduler. A DAG can be represented in a diagram like this one. The nodes represent tasks, the things you want to run, and the edges, the dependencies. A DAG scheduler executes each task in the appropriate order, waiting for its dependencies to be completed before running the task. However, our problems are often cyclic in nature. The blue arrows in this graph introduce loops into it, which mean that it is no longer an acyclic graph, but is now a cyclic graph. Cyclic problems appear in many domains, but especially in environmental modeling, where we're typically iterating in the time dimension. Cylc solves cyclic graphs by unrolling them. So this illustration on the right shows the first 3 cycles or iterations or repetitions of this DCG, with the blue arrows being the intercycle dependencies which stretch from one cycle to the next in order to string them together. Cylc is decentralized. There are 2 approaches to implementing a scheduler. With the centralized approach, a single scheduler runs multiple graphs or workflows in a single instance, whereas with the decentralized approach, one scheduler runs one workflow with multiple scheduler instances running in parallel. The decentralized approach is harder to develop as it requires logic for discovering and monitoring and controlling multiple scheduler instances. However, it does have some major advantages. With the centralized approach, as you add more workflows to the scheduler, you will eventually hit an artificial workload cap determined by the hardware you're running on, because it's relying on vertical scaling. Whereas with the decentralized approach, there's no artificial workload cap and the system scales endlessly because it uses horizontal scaling. So the scaling limits of the scheduler apply on a per workflow basis rather than a per deployment basis. As each scheduler is isolated, this approach is also much more robust, as issues in one scheduler cannot spread to another. Cylc also has some distribution capabilities. Cylc can distribute scheduler instances amongst a pool of servers, and it can do so with load balancing algorithms. And it can also distribute jobs across multiple submission nodes. Cylc also installs required resources for jobs onto remote file systems. Cylc is open source. Cylc started at the New Zealand National Institution of Water and Atmospheric Research, NIWA, and is now developed by an international collaboration, including NIWA, the Met Office, and others. Cylc can be installed via Conda and pip. So, to start with Cylc, let's pick the time-honored tradition of Hello World and write an example directed acyclic graph with Cylc. On the left, we have the Cylc configuration, and on the right, we have a graphical representation of it. First, we define the graph. Here, I've defined some tasks and given them each a single letter name, and the arrow symbols represent the dependencies between them. So the highlighted text on the left defines the graphical representation on the right. R1 tells Cylc that we want it to run this graph once, and the script setting tells Cylc what I want each task to do. In this case, I've configured all of the tasks to run the script echo hello and then the task name. That will that output will be captured into a log file, but this script could run anything from an echo script to a numerical model. This is a simple workflow suitable for running a collection of interdependent tasks. You might use a pattern like this to solve a data pipeline problem, for example. But what if we wanted to turn this into a cycling workflow? First, we will tell Cylc that we want it to number our cycles by setting the cycling mode to integer. And then we tell Cylc to start counting from the number 1 by setting initial cycle point equals 1. The graph on the right now shows the first 3 cycles of this workflow, labeled 1, 2, and 3. We then change R1, meaning run once, for P1, meaning run every cycle. And we need to tell Cylc a little bit about the dependencies which span between cycles, the intercycle dependencies. The square brackets minus P1 bit means from the previous cycle. So B minus P1, arrow B, means that the task B is dependent on its previous instance. So now we have a cycling workflow that's suitable for solving a repeating problem. For example, processing a data set in chunks. But in environmental modeling, our problems are typically cyclic in time. So what if we wanted Cylc to count its cycles with times rather than numbers? We would change the cycling mode to use the Gregorian calendar. And we also need current time. Next, we change P1, meaning a period of 1 cycle, to P1D, meaning a period of 1 day. This workflow is now running in simulated time, repeating every day. This might be useful for a climate study where you're running over a range of dates, perhaps using archived data, and want that to run in simulated time rather than wait for the real time. But what if we wanted this workflow to run in real time? We would add a dependency on wall clock to the first task in each cycle. Wall clock refers to the real time. It's a pseudo dependency built into Cylc. So now we have a workflow which would be suitable for a real-time monitoring system. So we've now taken the same workflow through 4 different modes of operation: acyclic, integer cycling, simulated time cycling, and real-time cycling. With Cylc, we aim to make it easy to start with a simple example and to grow the configuration into as an advanced pattern as required. So I'll now talk about some of the features and characteristics of the Cylc scheduler itself. This is a simulation showing how Cylc runs a cyclic graph, which demonstrates some of its features and capabilities. First, you'll notice that Cylc doesn't wait for 1 cycle to complete before moving on to the next. It runs tasks in multiple cycles simultaneously. As this workflow evolves, some of the tasks are lagging behind others. Cylc runs as far ahead into the future as it's able to run as much as it is able to at a moment in time. So it makes as much progress through the workflow as possible. But to prevent it from getting too far ahead, I've configured a run-ahead limit of 5 cycles. What this means is that Cylc won't run any tasks that are more than 5 cycles ahead of the slowest cycle. This allows us to run long-term systems without having to worry about excessive job submissions in future cycles. For date-time cycling workflows, you could configure your run-ahead limit as a date range. So rather than 5 cycles, you could say 5 days. Cylc does not load the whole graph into memory in order to run it. It constructs a moving window over the workflow. And just as this diagram is slowly panning to the bottom right, Cylc's window considers only the active tasks in a workflow. This means that Cylc can handle large workflows very efficiently, but also that workflows can be infinite. In order to respond to external events, you can use X-triggers, which are little Python functions that plug into Cylc, allowing the scheduler to be made aware of external events. And although Cylc uses a decentralized architecture, you can allow a collection of independent schedulers to interact by using inter-workflow triggers. Cylc also has an internal queuing mechanism that allows you to control parallelism and avoid flooding your job submission system. Cylc supports branched graphs. So in this example, Cylc will follow one of 3 paths through the graph depending on the outcome of the first task. So the first task can generate one of 3 outputs, X, Y, or Z, and Cylc will follow that pathway through the graph to the task B. This pattern can also be used for automated failure recovery systems. And Cylc has built-in stall detection, which means that it will alert you if the pathway through the graph becomes blocked, say by a task failure, or if a required task output isn't generated. Cylc uses ISO 8601 recurrences to define the schedule that your tasks run to. So I've got 3 examples of those here. The first would schedule a task to run every day, the next every day except every 3rd day, and the 3rd one would run every hour at 12:30, but only on the 1st day of the month. These recurrences can be combined to create more complex sequences, and you can have different parts of your workflow running to different sequences. So for example, you could have one task running every 5 minutes and another task running every 5 years. It's possible to write intercycle dependencies between recurrences, so you can tie all of that together into a single graph. Cylc supports the Gregorian calendar, but also the 360, 65, and 66-day calendars often used in climate research. And to make it easier to work with cycling systems and to develop your jobs into that pattern, Cylc provides some date-time arithmetic utilities, which also work with the climate calendars. So there are 2 examples here. The first takes a date time and adds 2 durations to it as offsets. The second lists the first 3 dates on a recurrence. Cylc can run jobs locally on the machine that the scheduler is running on, but typically we submit our jobs to a remote batch system in order to take advantage of a larger resource. Cylc has built-in support for PBS, Slurm, LSF, and a few other batch systems. But it also provides a generic interface for defining integration with other job runners if yours doesn't have built-in support. Next, we'll take a look at how we interact with Cylc workflows. Cylc supports a rich range of interventions and controls for both development and production purposes. Firstly, the workflow definition can be reloaded at runtime, so you can add and remove tasks and even change certain aspects of the graph structure whilst the workflow is running. But for more targeted editing, task configuration can also be edited on the fly. This means, for example, an operator could make a temporary change to the configuration of a task that applies only to one cycle or to a range of cycles. This is useful for responding to events in real time. Although Cylc uses a decentralized architecture, you can still perform interventions on a group of workflows or even a group of tasks within a group of workflows with a single operation. And workflows can be held back and released, allowing you to pause part or all of a workflow, which might allow you to, say, stop the workflow from doing anything for a few minutes to allow you to go and make some changes and reconfigure it before you resume the workflow running. Dependencies and outputs can be manually overridden. So if a workflow encounters problems, you can take direct control over Cylc scheduling, which allows you to fix problems by hand or fix the data using processes outside of Cylc, which provides operators with a lot of flexibility to address problems or use workflows in development modes. And workflows can also be rewinded and entire sections rerun. So for example, if a problem goes undetected and you need to go back a few steps, make a change, and then rerun a group of tasks in order to recover, Cylc can do that. It might also be useful if you want to go back a few steps and change a task configuration and then rerun everything downstream of that in order to see how that would change the results. So all of these interventions can be performed on the command line, but alternatively, they can be performed via one of Cylc's user interfaces. Firstly, we have a terminal user interface, which provides a simple command line interface which runs out of the box. This is highly portable because it just runs in a terminal instance, so it can run in HPC environments where you might not have a web browser installed. It allows you to monitor a workflow using a text-based view, which shows you active tasks and cycles within a single workflow. It also gives you the status information of them in a graphical form. You can view job submissions. So you can see the platform, the job's running on, the job ID, and timing information about when it's submitted or started to run. And you can perform some basic interventions. So for example, you could kill a running task or trigger a task to tell it to ignore its dependencies and run ahead of time, or you could start or stop a workflow. But Cylc also has a graphical user interface, which runs in the browser. This lists workflows and displays their statuses in this column on the left. And it has a text-based view very similar to the terminal user interface, which shows the cycles and tasks in a workflow. But there is also a graphical representation of the workflow structure that's similar to the diagrams I was showing you earlier. There's also a sortable table displaying job submission information, and you can stream the job output files in real time, so you can monitor not just the tasks, but actually the job submissions and see the output that's coming out of them. The GUI has full support for all of the command line interventions. We're currently working on a workflow analysis view, which will help you see how your tasks are performing by giving you some analysis of task runtimes, and there are more views planned for the future. The Cylc GUI is implemented as a Jupyter server extension, which means that you can run it alongside Jupyter Lab in the same server instance, or any other Jupyter server extensions. For multi-user setups, we have the Hub, which is a way of deploying the GUI powered by Jupyter Hub. This is useful for multi-user site installations. The Hub will start GUI servers for users on request, and it has an authorization layer which allows users to be granted permissions to perform selected operations on workflows that are running under other user accounts. So this is useful for situations where you have teams of people who are working on the same workflows, maybe a group who are working on a common workflow, or maybe an operational productional team who need to maintain a service. If you have an existing Jupyter Hub deployment, perhaps for serving Jupyter Lab, you can install the Cylc GUI into the Jupyter Lab environment and serve both Jupyter Lab and the Cylc GUI simultaneously from the same instance. Cylc is a production-grade scheduler. It has been used in production for 13 years. Workflows can be stopped, restarted, and resumed any number of times. Cylc will maintain the workflow state and can reconnect to running jobs when it's restarted. You can also start and resume a workflow from any arbitrary point in the graph, which is useful for recovery scenarios. Cylc can be configured to automatically retry any jobs which failed to submit or to execute, and there's support for modifying the task configuration automatically for retried tasks. So for example, if you have a numerical model and the model run fails due to an instability, you could configure it to retry automatically with a shorter time step to give it a chance of passing without the need for operator intervention. Cylc jobs communicate their progress back to the scheduler, which is how Cylc knows when they start running and when they complete. This communication can operate over TCP or SSH. However, Cylc can operate in the absence of two-way task communication if necessary by polling the jobs for their status. Even when communications is available, Cylc will still poll jobs occasionally in order to make it robust against critical failures, power out scenarios, batch scheduler failures, and network issues. Cylc understands that multiple nodes could be used to submit work to a single queue, and it can distribute its submission workload between them. If multiple nodes are configured and one goes down, Cylc will automatically switch to using the others, which allows for more interruption-free maintenance of submission nodes and potentially support for elastic systems. Workflow and job lifecycle hooks allow for integration into higher level monitoring and telemetry systems. So if you have an existing monitoring system, you can feed Cylc events through into it using these hooks. Cylc workflows can be easily changed between running in simulated and real time, which makes the job of getting research into production a bit easier because you can use the same workflow configurations for both, just with a small switch that adds the wall clock dependency into the graph. And Cylc has demonstrated scaling to hundreds of recurrences, thousands of tasks, and tens of thousands of dependencies per scheduler instance. Combine that with the horizontal scaling thanks to the decentralized architecture means that you can very quickly build up Cylc into a high throughput setup. There are also efficiency enhancements such as batching job submissions, which help to reduce the load on the submission systems that you run your jobs through. There is a list of sites who've contacted us to say that they're using Cylc on the Cylc website. If you are using Cylc at your site, but you haven't contacted us or aren't on that list, please get in touch and we can add you to it. So now we'll take a quick look at how the Met Office uses Cylc as a case study. Cylc has been used for research since 2012, and it's been used in production since 2014. This graph shows the trend of research usage from 2014 onwards. The yellow line is the number of simultaneously running workflows, and the blue line is the number of unique user accounts that are running those workflows. So these days, we typically have around 200 scientists running about 800 workflows. There's quite a bit of fluctuation in there. We use Cylc to distribute these workflows onto a pool of 12 workflow servers, which allows us to keep the load nice and even across them. The bulk of that workload is submitted to 3 Cray XE40 platforms, which collectively represent, I think, a bit under 500,000 CPU cores. They receive about 10 million job submissions every month, and 99.6% of those submissions are made by Cylc. Our next HPC platform is currently provisioned, which will initially represent in the order of 1 million cores and will involve hybrid cloud elements. We will be using Cylc to manage the workload on this platform too. Cylc is used as a general purpose tool for a variety of purposes. We use it for things like production weather forecasting, but also climate research and space weather. It's also used as the basis of the ROSTEM test framework, which is used for testing our numerical models, and a variety of other applications too. I was made aware a while ago that someone was using Cylc to download their pay slips for them. We use Ginger 2 and Rose to allow us to configure our workflows. This allows us to pull out key values and configure them in a separate file, or to configure different modes of operation, say case study and development, or research and production. Cylc has built-in support for Ginger 2, and support for the rows configuration system is available via a plugin. This is a little section of one of our production workflows. And if I just zoom out, you can start to see a little bit more of the structure of that. And if I zoom out again, these workflows can be quite complex. They can be quite simple simultaneously. We have quite a variety of different uses of Cylc. Some of them form quite advanced patterns, some of them stick to more simpler modes of operation. So that brings us to the end of this quick overview of Cylc. All of the Cylc projects can be found on the Cylc GitHub organization, and our documentation, which contains tutorials and a user guide, but also reference material, within which you'll find implementation details and architecture diagrams, which are particularly useful if you're interested in finding out more about the multi-user setups. And that can be found on cylc.org. The Cylc developers and the wider Cylc community can also be reached on our discourse forum. Feel free to drop by there with technical questions or workflow design questions. And for anyone who's interested in Cylc development or the implementation details of Cylc, there's a developers chat on Element, who anyone is welcome to join. Are there any questions?